Okay, so now we learned the basic rules of series network and parallel network. Now, most of the practical applications, the resistors will be connected in a slightly more complex way, that is called series parallel circuit. So there will be a combination of series connection as well as parallel connection to a single network. So let us see some examples of series parallel circuit and how do we do the analysis of series parallel circuit. If you combine a series circuit with a parallel, we can produce a series parallel circuit. Let's have an example. So here you can see R1, R2 and R3. There are three resistors, but R1 and R2 are connected in parallel. Then the combination of that R1 and R2 is connected in series with the third resistance R3. Now the analysis begins with finding out the total resistance of a series parallel network. So how do we solve this? We have to do the solution by a step-by-step analysis. First, consider in this example the parallel combination of R1 and R2. So by using the rule 1 over R total is equal to 1 over R1 plus 1 over R2, the equivalent resistance of R1 and R2 can be found to be 15, approximately equal to 15 ohms. Now, this combination is represented by 15 ohms. That is connected in series with the 58 ohm. So the total resistance will be, because they are connected now in series, 58 plus the earlier value 15.049. So the total resistance of this series parallel combination is calculated as 73.049 ohm, approximately equal to 73 ohms. I hope the calculation is clear. Now, in a series parallel network, we often have to do more analysis, like we may have to find out many currents and many voltages. So here we can see there is a total current. Total current gets divided because there is a parallel branch, and on the other junction this branch currents again combine together to form or to get back the original total current. So we have to now find out the total current and the branch currents. Also, there will be a voltage drop across each of these resistors, which could be different, V1, V2, V3. So we have to do the calculation of these voltages as well. So to begin with, how do we calculate the total current? Do you remember that we already calculated the total resistance and we have the total voltage? So all the calculation is followed by Ohm's law and remembering the rules of series and parallel connections. So let's start with the calculation of the total current, which will be I total is equal to V total over R total. This is nothing but Ohm's law. V total is given here as 100 volts and R total was already calculated as 73 ohms. So this calculation gives you a number 1.369 ampere. So this is the total current entering the circuit. Now, how do we calculate the branch currents? Don't forget that these R1 and R2 are connected in parallel, and if you remember, the current divides, and we can use the current division rule to solve or to find out the value of the individual branch currents. So let us find out the individual branch currents by the rule, current division rule. So if you want to calculate I1, the equation is I total over R1 plus R2. Don't forget, multiply with R2, the second branch. Substituting the values, this current will be equal to 0.763 ampere. In a similar way, calculating I2, the difference is we use here the first resistance R1. The calculation gives 0.606 ampere. If you add the two currents, you can find that you will get the total current, which is equal to 1.369 ampere, which is in fact the same current which we calculated as the total current. Now, coming to the calculation of individual voltage drops. Since we have all the branch currents, calculation of the voltages will be just applying Ohm's law. V1 will be I1 multiplied R1, V2 will be I2 multiplied R2, and V3 will be I3 multiplied R3. Now, if you calculate V1 and V2 with the proper values and their substitution, you can note down here that automatically the voltage comes as 20.6 for both V1 and V2. That is once again making the idea clear that the voltage across parallel elements will be always the same. Coming to V3, again the rule I3 multiplied R3, and you get the value by substitution 79.4 volts. Let us check one more point here. 20.6 is the voltage of the parallel branch and 79.4 is the voltage of the series element. Now, if you add the two voltages, you will get back 100 volt, which is the total supply voltage. The total supply voltage gets divided into the voltage for this element as a whole and the voltage drop across the third resistance. Okay, so with the help of this example, I hope your idea about series connection, parallel connection, and series and parallel combination is clear now. We will solve more examples in the class. Thank you.